Few infrastructure projects have been as technically ambitious and politically charged as the Chunnel Tunnel. What today appears to be a routine train connection between London and Paris was, for nearly 2 centuries, a vision suspended between bold imagination and geopolitical anxiety. A tunnel beneath the English Channel, 50 kilometers in length, excavated beneath the seabed, engineered to resist the relentless pressure of the sea, constructed with such precision that 2 excavation teams, advancing from opposite shores, would meet in darkness, deep below the ocean floor. This is the story of a project that became a symbol of European cooperation, financial overconfidence, and extraordinary engineering accuracy. An idea far ahead of its time. As early as 1802, the French engineer Albert Mathieu Favier proposed the fixed link between France and England. His concept was visionary but technologically unrealistic for the era. Horse-drawn carriages would pass through an illuminated tunnel, with ventilation shafts rising from an artificial island positioned mid. Throughout the 19th century, exploratory borings were undertaken, yet each attempt was ultimately abandoned. The primary resistance was not technological but military and political. For centuries, the channel had served as a natural defensive barrier. A permanent connection was viewed as a potential invasion route. Only in the latter half of the 20th century, amid a climate of increasing European integration, did political attitudes shift. In 1986, the Treaty of Canterbury was signed by Margaret Thatcher and Francois Mitterrand, formally approving the project. One decision was particularly significant. The tunnel would be financed entirely by private capital. No direct government funding would be provided. This approach reflected the economic philosophy of the 1980s, but it would later expose the project to severe financial strain. The geological challenge, the central question, was not whether engineers could bore a tunnel, but where it should be located. Beneath the channel lies a geological formation known as chalk marl, a dense and continuous layer of limestone extending from southern England to northern France. This stratum possessed crucial characteristics. It was stable enough to prevent collapse, yet sufficiently homogeneous and relatively impermeable to water. The tunnel was constructed approximately 40 meters beneath the seabed, at a maximum depth of around 75 meters below sea level. The total length of the Channel Tunnel is 50.45 kilometers, of which 37.9 kilometers lie beneath the sea. At the time of its inauguration in 1994, it was the longest undersea tunnel in the world. Construction and precision construction commenced in 1988. 11 tunnel boring machines were deployed, 6 from the British side and 5 from the French side. Each machine measured approximately 200 meters in length and weighed up to 1,100 tons. The cutting heads, equipped with hardened steel discs, rotated continuously through the chalk model. Progress averaged around 15 meters per day. Immediately behind the cutting head, prefabricated concrete segments were installed, forming circular rings that reinforced and sealed the tunnel lining. In total, more than 700,000 concrete segments were used. Each ring was fitted with rubber gaskets to ensure watertight integrity. The Channel Tunnel consists not of a single bore, but of 3 parallel tunnels, 2 main rail tunnels, each approximately 7.6 meters in diameter, and a central service tunnel with a diameter of 4.8 meters. The service tunnel functions as a maintenance corridor and emergency evacuation route, connected to the main tunnels by cross-passageas every 375 meters. The breakthrough moment, the most critical milestone, occurred on December 1, 1990. After months of precise navigation using laser alignment systems, gyroscopic guidance, and geodetic reference measurements, the British and French excavation teams approached one another beneath the seabed. Over a distance of nearly 38 kilometers, even the slightest miscalculation could have resulted in a catastrophic missile. Yet when the final barrier was breached, the horizontal deviation was only 36 centimeters, and the vertical deviation merely 8 centimeters. This level of accuracy remains one of the most remarkable achievements in modern civil engineering. The official opening took place on May 6, 1994, attended by Queen Elizabeth II and President Francois Mitterrand. A concept once dismissed as utopian had become a functioning reality. Financial reality. Technically, the Channel Tunnel was a triumph. Financially, it was initially a severe setback. The original cost estimate stood at approximately £4.7 billion. The final expenditure approached £9 billion. The increase was driven by underestimated complexity, enhanced safety requirements, construction modifications, and escalating interest payments on borrowed capital. The operating consortium, then known as Eurotunnel, faced substantial debt for many years. Shareholders experienced significant losses. In financial circles, the project was frequently cited as a cautionary example of overly optimistic revenue projections. Only in the early 2000s did the operation begin to stabilize as passenger and freight volumes gradually increased. enabling the tunnel to achieve sustainable economic performance. Operational significance today. Multiple categories of trains operate through the Channel Tunnel. The most prominent is Eurostar, connecting London with Paris and Brussels. Within the tunnel, trains travel at approximately 160 km per hour, while higher speeds are achieved on dedicated high-speed lines beyond the tunnel. In addition, the shuttle transports private vehicles, coaches, and heavy goods vehicles beneath the channel in roughly 35 minutes. Annually, more than 10 million passengers use the tunnel, and approximately 1.6 million trucks are transported through it. The link has become a vital logistical artery between the United Kingdom and continental Europe. Safety and incidency. Subsea tunnel of this magnitude demands rigorous safety systems. Since its inauguration, several significant fire incidents have occurred, notably in 1996, 2006, and 2008. The three-tunnel configuration proved invaluable during these events. The central service tunnel provides a secure evacuation route, while advanced ventilation systems employ pressure differentials to prevent the spread of smoke. The structure was designed to withstand prolonged fire exposure and is equipped with comprehensive monitoring, detection, and emergency response systems. A lasting symbol. Channel Tunnel represents more than infrastructure. It embodies political determination, technological innovation, and the willingness to undertake immense financial risk. Even in the post-Brexit era, the tunnel remains a strategic corridor for trade and mobility. Each train that passes beneath the channel reaffirms a fundamental principle: that natural barriers, however formidable, can be overcome through human ingenuity and disciplined engineering. What began as a speculative proposal in 1802 became reality nearly 2 centuries later. 50 kilometers beneath the sea, constructed with centimeter-level precision, sustained by ambition, perseverance, and a profound belief in progress.